Yeah, hot glue gun is.
Yeah, I'm not doing it. It says hot glue gun. Dildo is. It comes back.
Well, even better, the net force is zero, right? So there's no force on the system at that instant. And I think that's what we're trying to say with being at equilibrium. All of these things are true, and I think they all play a role in what they're going to ask us about in this particular example. So beyond that, block Q lands on block P precisely as it passes through equilibrium. So let's keep going because I don't want to lead you too much. The next part of this says block Q immediately sticks to the top of block P. And that idea, immediately sticks, means we're talking about at the instant it's at equilibrium, block Q sticks to block P, and the two-block system oscillates with a new period and a new amplitude. So the first question, I don't think is too terrible, but I'm going to let you guys take a look at the first question, and then in a few seconds, I'm going to hit one or two of you up for the answer. So here's the first question. Determine the numerical value of the ratio of the new period to the old period. All right, take 2 or 3 minutes, no more than that, and I'm going to hit one or two of you up for this answer. So they specifically want you to figure out by how much is it going to change. But it shouldn't be too hard to put the pieces together that if the object's inertia suddenly increased, then I would suddenly have a slower system. It's harder to move. Nothing about the spring has changed at all. But suddenly my mass went from m to 3m. So it has 3 times the inertia. Now, doing the work is not a whole lot here, but because I know some of you struggle with this, I do want to take a minute to talk about the work you needed to do. So if you think about it, they wanted the ratio of TPQ to TP. And keep this in mind, it's just a ratio, but you do have to know how to calculate period. My expectation is that part you can look up, you can have it in front of you. So that's 2 pi times the square root of m over k. Now you'll notice I wrote everything in there except for m. I'm doing it on purpose. This one, the mass was just m by itself. But this one, the mass was 3m. Now this is a slightly different way to do the problems where we have a change in a variable and we're trying to see the effect on the system. But that's because they specifically asked for us to do a ratio. So I want to make sure that we are doing the question that they asked. Sorry, I'm going to take a pause for a minute. So at this point, you still do the same procedure. You changed one of the variables, so you factor out the number part. And so here I'm going to factor out the square root of 3, and I'm still left with 2 pi times the root of m over k, all divided by 2 pi times the root of m over k, which clearly demonstrates that these cancel, leaving you with the actual numerical ratio, which is the square root of 3. That should have been your answer. Triple the mass, you get the square root of 3 as a change in the period. That number is clearly greater than 1, but not so terribly great. It's not like it's 3 times the period. It's just a little bit slower. So it takes a big change in mass to start getting an appreciable change in the period. This question probably was not worth very many points. In fact, I would be surprised if, based on the length of this AP question, if that was worth more than perhaps 1 point. Because then they go on and ask another question. And I'm going to try and leave the final question for a minute, but it doesn't look like I'll be able to do that, so here we go. I think we can. Can you read all of that in there? I think you can. It says the figure is reproduced above. How does the amplitude of oscillation of the 2-block system compare with the original amplitude of block P alone? Now, this is what Matt was trying to speak to earlier in the problem, but you got to choose if the amplitude is going to be smaller, equal to, or greater. Now, this is one of those questions where I don't know if the checkbox is going to get you any points at all, because it is immediately followed by in a clear, coherent paragraph length response that may also include diagrams and or equations. Explain your reasoning. Now, we don't have a whole lot of time remaining, but we have about 10, 15 minutes. I'd like your paragraph. I'd like you to think about this paragraph, because I think there's some things that have to be brought up, but I don't want to lead you too much. So I have to laugh, because sometimes when you look up and you're looking at people's, seeing what they're doing, you see things that surprise you, right? I'm just going to smile because somebody in this room knows exactly what I'm talking about. Last class period, I looked up, somebody was totally second knuckle city into their nose. Don't think they realized it. That's not what I saw this time, though. I saw something interesting. So here's where I'm going to stop. Problem was talked about. It says, in a clear, coherent, paragraph-length response that may also contain diagrams and equations explaining your reasoning. And if we go to the top, this is a 7-point problem, 13 minutes. So I'm kind of expecting that question A is probably 2 of those points, and question B is probably 5 of those points. That seems to be the way it's been separated in other problems like this. So in order to acquire these points, they're going to want to see a clear, I don't want to say concise because they're saying coherent, but there should be a progression from what happened and why it would cause the change you are suggesting. So first, in the participant window, raise your hand if you believe the amplitude will be less. All right, I think I got the picture there. And yeah, it should be less. Now, how you explain that, there is a variety of ways you can explain it. So let's talk a little bit about some of the options that you might have had available and maybe some things that you didn't. So first, and we're going to do yes or no. Did anybody mention net force on the block? All right, so our first round suggests no net force on the block. Next, did anybody mention conservation of momentum? All right, so we got 20 people say no, they didn't. Anybody mention conservation of energy? This one's getting a lot more upvotes than before. All right. Did anybody mention the change in inertia? All right. So I think that there's a lot of things that can be brought up here in order to successfully explain why the amplitude is reversed. It's whether you are successful in presenting that argument and connecting all of the dots. What I mean by that is, I think you need to start from the beginning, that the first block landed on the second block. Here, let's take tell you what, I'll post it for you guys, okay? Because this is gonna just knock me out here any second. Either way, guys, it looked like you guys are working nice and hard. I do appreciate that quite a bit. As always, it's been great to see all of you today. I hope you guys have an excellent afternoon. Looks like the sun is finally starting to come out there, so definitely get outside, get some sunshine, get some rays, get some exercise. And I hope you like tomorrow's video. It's not funny, but it took a lot of time for me to record it. I think it's pretty cool. So we're going to start getting into circular motion tomorrow. All right? So have a page out of this. We had, in the first case, we have this block traveling on its own, mass m. It is at its max velocity at equilibrium. And then suddenly, the other block lands on it, so our mass goes to 3m. If you didn't think this was a collision, that's too bad. It certainly is a collision. And you could treat it like a perfectly inelastic collision, where the momentum before would have to be equal to the momentum after, and we have m times v for the momentum before, v max, has to equal m plus 2m times v final. You could have done it that way. You would have figured out immediately that the new velocity is a third of what it was before. Now, once you know that it's traveling slower, you know it has less energy. And once you know it has less kinetic energy, you know it's going to have less potential energy. You could have made that statement. That connects all the dots together. But notice, in order to use this argument, you have to use momentum suggesting a change in velocity. And then you have to suggest that that change in velocity produces a change in the energy of the system. But you don't have to do it this way. There's certainly some other ways you could have done it. There's a single relationship that you might have been able to throw down as your support. Right? Does this look familiar to anybody? Because if the velocity changed and this didn't change, then the only other thing that would have to change would be the amplitude. There's absolutely no reason you couldn't have made this argument, but then you still would have had to have explained how did the velocity change? And it got less. But you don't need to do any of these. There's still every reason to consider that force would have worked just fine. We know that the force acting on the box has got to be equal to MA. K of the spring doesn't change. M certainly does. That suggests that if M gets bigger, the acceleration has to get less, and the force in the spring remains. It's going to be harder to change the block. But you still need to consider that that works, that explains part of it. It just doesn't explain the collision part where velocity was lost due to the collision. And that part, I think you really need to make sure you hammer home. That there was a change in velocity the moment the one box struck the other. Now look, if I wanted to give you a neat quiz, if I wanted to find a way to tie this together, you know what I would do? I would give you the exact same question, except in this new version of the question, I would have the box drop on the second box. This is some messy pictures going on here. I would have the box drop on it at the maximum amplitude and ask how this would change the system. It's a similar question, and this question was asked 2 years earlier. If we look at the last couple years, they asked the question this year where they dropped the box at equilibrium, and 2 years ago they asked the question where they dropped the box at the max displacement. They're similar questions, but the results are different. But listen, we are on our last minute and a half, so they're gonna end this meeting on us. Please make sure you try to give me your paragraph. I want to see the kind of stuff you guys said. Tomorrow, we're going to look at the table reading notes for this problem to see what the judges were looking for. This is not the grading guidance. This is different. Kieran, you have a question?